are L time constants. And in an RL time, there is something called an RL. What is L? L is your inductor. I will have here, let's say I have a voltage source. I will have a resistor. I will have a coil. That's a symbol for an inductor. I will have a switch. Like so. And so this will be L1. This will be R1, this will be S1, and this will be VS. So here's an interesting property. Inductance property of building a magnetic field around a conducting wire, period. That's one definition of inductance. Inductance can be thought of as the property of building a magnetic field around a conducting wire. So with any wire, if I have our multimeter leads, for example. So here's a pair of multimeter leads. And if I were to hook this up on a battery pack, so here's my battery pack. If I were to hook that up to the battery pack and pop in the third battery and measure the voltage between these two, there will be current that is flowing through the red and black wires. The electricity will flow out through the black wire, the net electrons will flow out through the black wire, get connected to my voltmeter, like so, and then the voltmeter will read the amount of that electricity flow, and based on circuitry in the voltmeter and the electricity that comes back to the positive wire, it will make a determination how much voltage I have in the battery pack. You've done this many times with your digital multimeters to measure voltage. But one thing that we hadn't talked about is in any wire that carries electricity, there will be a magnetic field that builds around that wire. It's a property of we call inductance. So here we go. As a magnetic field is built around the conducting wire, we can concentrate that magnetic field by winding the wire into a coil. Okay, so a coil equals concentration of inductance by winding loops, of wires onto each other. So the coil allows us to concentrate the inductance simply by winding the loops of wires onto each other. I have wire. If I make a loop like so, the magnetic field of the first loop will interact with the magnetic field of the second loop and will increase this property of electromagnetism. And then if I do this with another loop, and I do this with another loop, and I do this with another loop, and I do this with another loop. So what I've gotten are the same size loops, same as I can make it in this illustration. And if I have electricity flowing through this wire, because I've now wound this wire into loops and have these loops the same size diameter and have them intimately close to each other like so, I have increased the property of inductance where this is now a useful thing. By making loops of wire in this fashion, I've now created something called an inductor. The property is called inductance. Winding them into a coil concentrates that inductance. And by creating a device that is multiple loops, I have created something called an inductor. An inductor is an electrical device that we use in electronics very often, and it's shown in the schematic symbol as coils like so. And I'll show another illustration of them in a moment. But this is how an inductor is very easily made. Now, like capacitors, weren't there different characteristics of capacitors that determine their capacitance? Didn't we talk about the size of the overlapping area previously? If I have capacitors with only this much overlapping area, I only have that much capacitance. If I overlap the area by this much, I have more capacitance. If I overlap the area significantly, like so, I will have maximum capacitance. So the amount of area of the plates onto each other determines capacitance. What else determines capacitance? Was the distance between the plates. So if I have one plate over here and I have another plate very close to it, I have pretty good capacitance. But if I start separating this, the interaction between the plates is less and less. So the closer I can get these together, the more capacitance I will be able to achieve. And then the third component that affects capacitance will be the dielectric that's used in between. By the same token, we also have similar concerns with respect to inductors. So here I've made multiple loops of wires into a coil. So one of the key factors that determines capacitance is going to be the diameter of my coil. The smaller I make that diameter, the more concentrated the magnetic field will be. Did you hear that? The smaller I make the diameter, the more concentrated the magnetic field will be. Well, this is about a 1-inch diameter. So if I were to decrease that diameter to half of that, if I were to wind all of this, say, around a pen, for example, like so, like so, like so, like so, like so, like so, like so. Wow. Is my diameter now noticeably less than what it was before? Yes. So by making the diameter smaller, I am concentrating the magnetic field. Therefore, I am increasing the inductance of my coil. Another property that affects, in addition to the cross-sectional area, the diameter which gives us the cross-sectional area, is the spacing between the coils. If I have a loose space between the coils, and this has to be uniform, and I can't do this very well with this demonstration, but if I have space between the coils where the wires are, where the hoops are not intimately connected with each other, I will have less inductance. If I jam them up, one right next to the other like this, and there's no air gap between them, I will have maximum inductance. So two factors we've discussed so far that affect inductance. One would be what? One would be what? Question goes to Kyle. What is one factor that affects inductance?
How close the coils are together?
How close the coils are together is one. So if I pack them up, they're really close, I will increase capacitance. If I space them out, I will have less capacitance. What is a second factor that affects capacitance? Mr. Cortez.
The diameter of the radius of the coils.
The diameter of the coil. The radius is half of the diameter.
Yeah, right.
So the same idea. So by making the coil physically smaller, I am concentrating the magnetic field. So this coil wrapped around my pen, as opposed to the first one that I made wrapped around, say, an imaginary 1-inch object, this will have more inductance because we have concentration of the magnetic field. There is a third factor. The third factor has to do with the material that we use in the core of the coil. In other words, if I put something in here, if I create this coil and I pull the pin out, I have air in here, yes? If I have air in there, that's called an air core coil, meaning the core of this set of loops is hollow, so the core is made of air. I can concentrate the magnetic field further if I put something in that core. And what's mostly done in the industry is going to be an iron slug, a rod of iron, because a rod of iron not touching the coils but placed inside the coils will concentrate the magnetic field even further and will affect the amount of inductance that you're going to realize for this coil. So those are the three things that affect the coil: is the type of material that is used in the diameter, and then also how tight the windings are. And I'll go ahead and release all of this. So let us say that this guy is equal to, let's say, 270 lowercase m capital H. So the device that we're talking about, the actual device, is called an inductor. It has another name. It could simply be called a coil. It could also be called a choke. There's a descriptive, they're called chokes, coils, or inductors, okay? So those are the name of the devices. The units equals H, which stands for Henry, named after the famous scientist who advanced the scientific papers to the community explaining all of this. So it's named after Henry, just like ohms was named after Mr. Ohm, and watt was named after Mr. Watt, and volt was named after Alessandro Volta, and amps is named after Andre Marie Ampere. So this is named after Mr. Henry. So that's why we have a capital H for millihenry. Is everybody okay with 270 lowercase m, H, 270 millihenry? And let me give you the value for the resistor, and let's say the resistor is equal to 950 ohms. And this is also equal to 10 volts. Now, the time constant in this particular case is going to be an interaction between the L and the R, and it happens to be L over R. L over R. We're not multiplying in this case, this is a division. And so in this case is equal to 270 equal to 270 millihenries divided by 950 ohms. So that's 270 exponent, change sign, and Wenbin, milli is what power of 10, my friend?
You know about 10?
Yeah, what power of 10?
Negative. 1 to 700.
Milli is -3. And then you're going to divide that by 950, and that will be equal to the time constant, and the time constant has units, and we'll go ahead and calculate that in just one moment. So let me go ahead and pop this in here.
1,842.
This is a divide, my friend.
Yeah, divide.
0.270 and divide by 950. So what do you have, my friend? Mr. Wenbin?
Oh, I can see. Two.
270 exponent negative 3 divide by 950.
2.842. 2,000. No. 2.842.
Wenbin, you should have calculated it times by now. What are you doing?
I used to do the 2.8 of 42.
Oh, hit engineering on your calculator, pal. You have it in scientific notation, so you got to put it in engineering notation. So what is it in engineering notation? Yeah, your number, I see what you've typed, and what you've typed is not correct. So I wrote down here, and if you follow this, 270 exponent negative 3 for milli, divide by 950, you should end up with 284.21, and the units are micro, because it's a 10 exponent negative 6 on the calculator, and time is measured in seconds. That's what you should have. Okay, Wenbin and everybody? Any questions about how to calculate the one-time constant? So yeah, you're gonna need a little more practice, my friend, on utilizing your calculator. And I'll do it again, 270 exponent negative 3, and then divide by 950. And that's what we have. Okay, so practice that until you are confident and comfortable with making the calculator demonstrate the correct result. Any questions does anybody have on the time constant? Okay, so here's the next question. Time for full, and I'll use the word charge. It's actually an incorrect word to use, but conceptually it's not bad. So how long does it take for this coil to reach its full magnetic capacity? Will be how many time constants? It works just like the capacitor before, will be 5 tau. So mathematically, we will do 5 times the 284.21 microseconds. And I'm looking for that calculation. If you can give me the calculation, please, Mr. Rolando. Time for the full magnetic field to develop.
Okay.
Rolando, do you have that number?
Okay, it's 1.42
1.42 what?
milliseconds.
Okay. So if you all go through this calculation correctly, and I'll take the chat off my screen because it's disruptive, you should end up with 1.42 milliseconds. So it's a lowercase m and a lowercase s. Is everybody okay with that time for the full magnetic field? So far, so good. Okay. Now, let me show you graphically what happens with respect to this on a time constant chart. So on a time constant chart, this is what we're going to have. I'll try to do this. Everybody turn off your mics, please. Thank you. Okay, so I'll try to do this a little larger.
Alright.
Would you turn off your microphones, please? Thank you. Okay, so we happen to have something like this. Okay. And let's go ahead and space this out. So I happen to have 1, 2, 3, 4, 5. So one will be here. Next one will be here. Next one will be here. Next one will be here.
Apenas los compré, o sea, aquel lo tiene como 2 años más, aquel, ya me creció así de tamaño.
My friends, could you please turn off your mics? Thank you. All right. So, time constant chart. 0, 1, 2, 3, 4, and 5. This is time in units of tau. It's also in units of seconds if you'd like. Up here will be 2 values. Up here will be a value for V, and up here will also be a value for I. And let's describe what happens. Let's describe what happens when this switch is closed. The moment this switch is closed, the coil will resist current flowing. The current will not flow immediately. The coil behaves as if it's blocking all the current. And if it blocks all the current, it is as if this were infinite ohms in series with only 950. So here's the things to keep in mind for a coil. Initially, coil opposes change of current. So all voltage is across the coil. And I can demonstrate this very easily by drawing a separate little circuit on the side here. I will draw this. Here's a resistor, and here's the switch, and the switch is now in the closed position. And here is the coil, and here's another way that I'm going to draw the coil. Okay, that's another way to draw the coil. And so initially, there will be 0 amps. Because what? The coil wants to do what with the change of current? It wants to oppose any change of current. So if it opposes any change of current, whatever I start off with voltage over here, if I have 10 volts over here, do I have any current flowing through the resistor? No. I have 0 amps here. I have 0 amps here. What is my voltage across the resistor at this particular moment? My VR, isn't that equal to I times R? Is that right? Isn't that how I calculate the voltage across the resistor? What is my I at the very beginning? The current at the beginning is 0 amps. So my VR at the very beginning is going to be 0 times 950 ohms. So what is my voltage on the resistor initially? 0 volts. Nothing, nada. So in this circuit, do I have a closed loop, yes or no? The answer is Yes. Here, do I have the ability for electricity to flow because I have a closed switch? The answer is yes. The ability is there for current to flow. However, a very unique characteristic of the coil is that it opposes any change of current. I'll say, well, wait a minute. What change are we talking about? Well, initially, if the switch was open, there is no current, yes? The moment we close the switch, is there a change of current that could occur? Yeah, current could start flowing. What does the coil do? It opposes that change. No current flows at 0 time. No current here means no voltage. Mr. Kirchhoff has to be happy. All the voltages in a closed loop have to add 0 volts. You know that from last week's discussion. Kirchhoff's voltage law says all the voltage in any closed loop algebraically has to add to 0. This is a negative, this is a positive, this is a negative, this is a positive, and this is a negative. Well, guess what? Initially, you will see you've got 10 volts right here. At the very beginning, the voltage is going to be green dot right there at the very beginning. At the very beginning, current will be red dot down here. So current is equal to 0 amps at the beginning. Your voltage is equal to max at the beginning. Okay? What happens over a period of time is this. The current will be allowed to flow because the characteristic of the coil, initially it opposes a change of current, but slowly it lets the current start to flow. So in the first time constant, that current will flow 63.2% of maximum. In the next time constant, the increase will be to here. In the next time constant, then the increase will be to here. And the next time constant, this will be here. Finally, we reach maximum current at the end of 5 tau. And this curve looks like so for current. So I now have I max at 5 tau. It started off at 0, and after 5 tau, current reaches maximum. At the end of 5 tau, this becomes nothing but a straight piece of wire as far as DC is concerned. What happens with voltage? We said voltage started off at maximum. At the end of the first tau, this thing will drop 63.2% of the maximum to there. At the next one, it'll drop to here. At the next one, it'll drop to here. At the next one, it'll drop to here. Finally, it'll drop to no volts because this behaves like a bare piece of wire. I will go to connect the dots. When I go to connect the dots, I end up with this, and now V is equal to 0 volts at the end. Can you make a concluding statement similar to what we had before? We made a concluding statement before, very important point. Current leads voltage or voltage lags current based on a capacitor circuit. Can we make a similar concluding statement here with respect to voltage and current? Rebecca, you want to give that a shot? What do you think you could summarize this with? And the wording will be similar to this. Something is going to lead something, and something's going to lag something.
Would it be that voltage leads current and current lags voltage?
How about that? So voltage leads current and current lags voltage. Okay, turn off your microphones. That's excellent. And if I can squeeze everything into my frame here. Does everybody agree on that summary statement? The voltage is at maximum at the very beginning of our time constant analysis, And then after 5 time constant, then the current reaches maximum. So voltage is said to lead current, or conversely, we could say current is lagging voltage because it happens 5 time constants later. Any questions on that? And if we go to fill in our time, our time in here was, each one of these increments was 284.21 microseconds. This is another 284.21 microseconds, such that at the end of 5 time constants, this whole process took 1.42 milliseconds. Sorry, that's right at the bottom. Didn't mean to write quite that small and that far away. Let's see if I can make this just a little bigger. I think I can get it in the frame. Okay, that's a good frame. So how do we contrast, before we go to do the contrast, is there any questions as to what we've done here so far? How do we compare and contrast the green line of a coil circuit, an RL circuit? The green line starts at maximum and goes down to 0. Okay, it starts where? At maximum and goes down to 0. How does the green line work for a capacitor circuit? The green line starts at 0 and then works its way up to a maximum, yes? This started at 0, works up to a maximum. The green line here starts at a maximum and goes to 0. Take a look at how current behaves. Current started at 0 because why? The coil opposes a change of current. So initially, the current 0 amps, 0, but after 5 time constants, that magnetic field will be such that it will allow current to flow. So the current starting at 0 after 5 time constants reaches maximum up here. How does this red exponential curve compare with the coil circuit compared to the cap circuit? Compared to the cap circuit, the red line starts at maximum and goes down to 0. So the concluding statements is going to lead us to a very profound mnemonic. What's a mnemonic? Who remembers what is a mnemonic? Pauline, you remember what is a mnemonic? M-N-E, mnemonic. You remember what was a mnemonic?
It's kind of like a rhyme that would make you remember the meaning of what it is that you're trying to remember.
That's a really good one. I like that
Just like,
definition.
Roy G. Biv is equal to the rainbow colors.
Yeah, I'll give you a simpler one, and I like this one because there's many different ways of putting together a mnemonic, but fundamentally, it's a memory tool. So there's ways we can use rhymes to help memory tools. We can use acronyms. We can use abbreviations to help us in memory tools. So a mnemonic is fundamentally a memory tool. So the RC time constants and how this is derived and RL time constants and how this is derived takes us to a memory tool called, right here, my black pen.
Guys, man.
Eli, the ice